Welcome to section 1.4. Here we are going to be talking about separable differential equations. So a first-order differential equation is called separable if it can be written in one of the following forms. So that is p of y times dy dx equals q of x. Or, using the concept of a differential, p of y dy equals q of x dx. So a separable differential equation essentially means just what it says. You can separate off the x's from the y's. You can separate the variables across the equality. Once we have the differential equation in this form with all of one variable on one side and one of the other and all of the other on the other side, to solve this, we must integrate both sides. Integrate both sides of the differential equation, and then we will have our solution. So let's take a look at some examples. Solve y prime equals y squared over x squared plus 1. So let's go ahead and set this up using that Leibniz notation, that dy dx notation. That equals y squared over x squared plus 1. Now, if we're going to separate these, so dy can stay over here. Dx, however, because it's in the denominator, it needs to come up. So it needs to come over to this side. So we need to do a little bit of rearranging here. So the dy will stay over here, equals y squared over x squared plus 1 dx. But we want this y squared to go to the other side, so we're going to divide it under to the other side. So this is going to be 1 over y squared dy equals 1 over x squared plus 1 dx. And this now has been separated, so we can go ahead and integrate. So integral of 1 over y squared dy equals integral of 1 over x squared plus 1 dx. Antiderivative of 1 over y squared is negative 1 over y. Antiderivative of 1 over x squared plus 1 is the inverse tangent of x. Now, both of these are indefinite integrals, so theoretically they would both need an arbitrary constant, a plus c. But because they're a part of the same equation, we could just consider that they were all put onto one side together. So we can just include a plus c on the right-hand side. Because it's arbitrary, it would all turn out the same way anyways. From here, if we want the solution, we need y. Right now we have negative 1 over y. So you can picture this algebraically however you want, like multiply the y over here, divide all of this under here, or just consider taking the reciprocal of both sides and multiplying by negative 1. However you want to think about it algebraically, we get y equals 1 over inverse tangent of x plus c. And that would be the solution to this differential equation. So anything that has this form for any arbitrary value of plus c here, we would take its derivative, and it should give us something that looks like this. I left off my negative, didn't I? Yeah, there should be a negative out in front of this whole thing. Right there. That's better. So when it comes to separable differential equations, the process overall should remain very similar from problem to problem. So the functions are a little different. The format, the setup is a little bit different. for each case by case, but the overarching process should be the same for all of them. And that is the idea that you want to separate entirely one variable from the other. If that's not possible, then this method is not the best way to go for that differential equation. So if we look at this next example here, solve 1 minus x squared times y prime plus xy equals 4x with the initial condition y of 0 equals 8. So let's go ahead and set this up with that kind of standard Leibniz notation. That'll help us with separable in particular. Equals, actually, let's move this other term over. I'm going to want to get these x's together, so we'll take 4x and we'll subtract off xy. Now we'll keep the dy over here. The dx is going to need to move over here. So we'll have 1 minus x squared dy equals 4x minus xy dx. And let's go ahead and factor that x out, actually. Because now we're just about ready to separate. So this 4 minus y term has to come over here. This 1 minus x squared term has to come over here. So let's divide both under. So this is going to be 1 over 4 minus y dy equals x over 1 minus x squared dx. And this is about ready for integration. So we can go ahead and just put that symbol on right there. So to take the antiderivative of the 1 over 4 minus y, that will have a natural log antiderivative, but because there's a negative in front of the y here, we would need to incorporate that. So we're going to get negative ln of the absolute value of 4 minus y. On the right-hand side, we do similarly. This will be a natural log antiderivative. You can set up like a u substitution for this. So with 1 minus x squared, and then the x up here will go with the dx. But it works out very similarly. We get negative 1/2 ln absolute value of 1 minus x squared, and then plus that constant c. We can go ahead and get rid of the negative on both sides. So we're going to need to solve for y, but we're also going to need to incorporate this initial condition. So let's go ahead and incorporate that now. So when y, well, let me re-put that here. So use y of 0 equals 8. So if we substitute in the appropriate values, x is 0, y is 8, we get ln of absolute value of 4 minus 8 equals 1/2 ln absolute value of 1 minus 0 squared plus c. So we get ln of negative 4 within the absolute value. So because of the absolute value, it's just ln of 4. This equals 1/2 ln of 1 plus c. ln of 1 is 0. So c is just ln of 4. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . So we can go ahead and incorporate that into here. So in this next step, so ln of absolute value of 4 minus y is 1/2 ln absolute value 1 minus x squared plus ln of 4. Now, in order to solve for y, we need to get rid of this natural log here. And the only good way that we have of doing that is by raising that into the power of an exponential function of e. But whatever you do to one side, you're going to have to do to the other. So on the left-hand side, that's going to undo the effects. So the e is going to go there. But all we're going to be left with is the absolute value of 4 minus y. And on the right-hand side, we have e to all of this. So e to the 1/2 ln absolute value 1 minus x squared plus ln of 4. We can go ahead and play around with that right-hand side algebraically a little bit. You have an addition here within the power. We can split that up into a product of the bases. So that's e to the 1/2 ln of absolute value of 1 minus x squared times e to the ln of 4. Now, for this one, the e and the ln cannot undo each other at the moment because this 1/2 is in the way. So what we need to do is we need to use the properties of logarithms and move that 1/2 up into a power. In doing so, we will have cleared the way for the e and the natural log to undo each other and get rid of each other, essentially. So that's going to be absolute value of 1 minus x squared to the 1/2. And here, the e and ln also undid each other. So that's going to be 4. Now we have this absolute value here on the left-hand side. We want to solve for y, so we need to get rid of that. In order to do that, we need to take into consideration that we could be taking the positive or negative values of this solution. So like if this solution produced like a positive or a negative, we would need to balance it out in order to maintain this relationship. So we have to keep this plus or minus here. We have two possible solutions, two possible cases. So on this side, we have the 4. This 1/2 power is the same thing as a square root. Absolute value of 1 minus x squared here. We can move this around a little bit. So we can like move the 4 and then multiply by -1, or you can move the y and move this term. Either way, we're going to get y equals 4 plus or minus 4 times the square root of absolute value of 1 minus x squared. Now, the plus or minus takes into account two possible outcomes because of the absolute value, but we know from our initial condition that y of 0 equals 8. And if we took 4 minus 4 times some positive number, that would result in a negative. So, or certainly something less than 4, right? If this was a fraction, it would be still positive, but still it would be smaller than 4. It has to be 8. So there's only one way that that works. So if this is 0, we get 4 plus 4, which is 8. So since y of 0 equals 8, the only solution is y equals 4 plus 4 times the square root of absolute value of 1 minus x squared. So we have here our particular solution for this differential equation found using this method of separable differential equations. Now, one differential equation that we have encountered before is separable, and that is the differential equation describing Newton's law of cooling. So here we're going to actually be able to derive the formula, okay, for that solution to Newton's law of cooling. So we're going to start off, so the t prime, so that's just going to be dt equals negative k t minus t sub m. And we need to separate, so this t needs to get onto this side over here. So we're going to go ahead and divide away that whole expression. We're going to get this dt over here, the d little t over there. So that's going to be 1 over t minus t sub m dt equals negative k dt. This is now separated. Remember, this t sub m is a constant. So we can go ahead and integrate both sides of this. On this side, we're going to get, similarly to the other problem, a natural log, absolute value of t minus t sub m. On the right-hand side, it's just negative k, which is a constant. So it's negative kt plus a constant, which I'm going to call c1, because I want the final equation to have c in it, and it's going to change a little bit. From here, we want to get rid of the natural log, so we raise both sides into the power of an exponential. So that cancels the log, and we're left with e to the negative kt plus c1, which, similarly to the last example, we can split up into product of the bases. So e to the negative kt times e to the c1. And this is where this change in variable is going to happen now, because e to the c1 is all constant. So instead of calling it e to the c1, we're just going to call it c. So this is c e to the negative kt. Because it's arbitrary, right? C1 is arbitrary, so e to the c1 is also arbitrary, so we're just calling it c for the sake of the formula, for the ease of it. Then to get rid of absolute value, we would need to incorporate a plus or minus. But again, the arbitrary nature of this constant really helps us out here, because whether it's plus or minus, the constant will adapt and it will adjust based on the plus or minus, so we don't need to include plus or minus in this formula. And from there, add t sub m to the other side, so we get t of t equals t sub m plus c e to the negative kt. And this is the general form of the solution to Newton's law of cooling. This is the solution to that differential equation that describes that relationship for Newton's law of cooling. We can use this solution to then solve problems involving differences in temperature and cooling. So in this example right here, an object whose temperature is 615 degrees Fahrenheit is placed in a room whose temperature is 75 degrees Fahrenheit. At 4 p.m., the object is 135 degrees. At 5 p.m., it is 95 degrees. When was the object put into the room? So, in order for us to answer this question, we need to fill in a lot of unknowns here. So we have a lot of pieces of information. In our formula, we need t sub m, we need c, and we need k in order to do this. T sub n we know. This is the room whose temperature is 75 degrees Fahrenheit. So that tells us T sub m is 75. we're going to go ahead and let 4 p.m., since it's the first time mentioned in the problem, we're going to let that be our initial time. So we're going to let t equals 0 be 4 p.m. And we'll go ahead and put t in hours here. So we know t of 0, so the temperature of the object at time 0 is 75 plus c e to the negative k times 0. That object's temperature was 135 degrees. So we get 75 plus c times e to the 0, so just plus c, equals 135. So c is 60. And then we still need k, but we also have one more piece of information. So at 5 p.m., it is 95 degrees. So 5 p.m., that would be after 1 hour. So t of 1 is 75 plus 60 e to the negative k times 1. That equals 95. So we can go ahead and subtract the 75 over and then divide by the 60. So we get e to the negative k equals, it was 20 over 60, so 1/3. Take the natural log of both sides to get rid of this e. So we're going to get negative k equals ln of 1/3. Now, you could just get k equals negative ln of 1/3, but there is a simpler way to simplify that. Because of the properties of natural logs, we can split this up into subtraction because it's a quotient. So we get negative k equals ln of 1 minus ln of 3. ln of 1 is 0. So we get negative k equals negative ln of 3, or in other words, k is ln of 3. So that's kind of the nice, fully simplified down version of k. Now, we have our general formula. We have all the pieces that we need. So that's 75 plus 60 e to the negative ln of 3 times t. Now, we are looking for when the object was put into the room. So we're looking for a time, so a t value here, when it was put into the room. The only thing we know about when it was put into the room is that it was 615 degrees. So we're going to take this equation, set it equal to 615 degrees. That was when placed in the room. And now we need to solve this for t. We need to find the time at which this occurred. So subtract the 75 and divide the 60. So we get e to the negative ln of 3 times t. It actually works out just to 9. So that's pretty handy. If we take the natural log of both sides of this, we get negative ln of 3 times t equals ln of 9. So divide that over to solve for t. So t equals ln of 9 over negative ln of 3. Now, to get some more specificity into this answer, we can play around with the logs just a little bit. So like ln of 9 is, well, let's get the negative out here in the front. Ln of 9 is the same thing as ln of 3 squared over ln of 3. And that square is on the 3, just for the record. But using properties of logarithms, the 2 can come down to the front. So we're going to get negative 2 ln of 3 over ln of 3. That provides us with the cancellation that we were looking for. So we get negative 2. This is a time in hours. So the question was, when was the object put into the room? Well, it was put in at a time 2 hours, so negative 2 hours, 2 hours before our initial time, which was 4 o'clock. So this is 2 hours before our initial time. So we can say it was placed in the room at 2 p.m. So we were able to solve this problem using the solution to the differential equation that we derived above, using the method of separable differential equations. So when we come back in the next sections, we will be looking at more types of differential equations and ways that we can solve those. But this has been our introduction to separable differential equations.